In this presentation of open automation software, we will learn the importance of IoT data accuracy. We'll see how OAS is used to collect data from industrial control systems, communicate data from the controllers, processors, .NET applications, any Industry 4.0 data source, collect that data and process it in a first-in, first-out queue processing, transfer the data across the network to user interfaces and also to other OAS edge solutions, and archive that data in a database in an open format. We'll see the advantage of running as an edge computing solution that's distributed across the network so that there is no data loss on a network failure or even a database engine failure. We'll see OAS use the store and forward feature that's built into OAS so that you'll see that there's no information loss on the trend information, alarm information that's processed locally, and of course the data logging. And we'll bring up visualization both in a web and a .NET interface, and we'll see that all data as it's processed on-premise would be available to the user with all accuracy. Now I'd like to demonstrate open automation software in action so you can see what kind of performance you would expect to achieve from it. So what I'm going to do is I'm going to configure a system, a remote system, that's a Raspberry Pi device. It's running the full OAS framework. I'm going to select that IP address. Just a point of reference, or the diagram we were referring to earlier, this would be the collection engine that would be obtaining the values from the controller or the data source directly. And then it's going to process locally on that system, on that Raspberry Pi device, all of the data to timestamp it with the correct timestamp, and of course process it through the complete engine to then deliver it to the remote engines and also applications. So let's just add a tag to that system. We'll just give the tag name A. And we're going to set its data type to a 32-bit integer with the data source of simulation, just to give us some changing values. I'm going to set the simulation rate to 1 millisecond. And so when we apply those changes, we'll see the value is now updating from that remote Raspberry Pi device. Now what I'm going to do is I'm going to switch to my local system. So we've got the data being processed from that remote Raspberry Pi device, and now I'm going to configure the localhost system that's running on a Windows system. So I'll set up some data logging here, and I'll select my local system. I'll set up a logging group name called test, and I'll change the data logging type to data change row. That is going to log a new row for multiple values anytime any of the values change. We'll leave the deadband at 0 so we can see all values that are changing. We'll set the date and time precision to be of a high format, high precision, so that in SQL Server we'll get a date time 2 with 100 nanosecond resolution. When we browse for a tag to add, what we're going to do here is we're going to specify what items we're going to log. And these can come from local or remote nodes. I'm going to select this remote node, the Raspberry Pi device, that tag we just created. And we're going to set the field type to something simple as a value, and set the data type again to a 32-bit integer. And under the database tab, we'll specify where we're going to log that to. Now, we can specify a remote database engine. I'm going to use a local one, but a remote one is just as reliable because OAS has built within it stored forward functionality. I'm going to log it to a database called testDB and a table called remote data. So we'll add that to the local configuration. And now we're logging values to SQL Server. We're logging samples at a frequency of 1 millisecond. But when we actually do the insert to the database engine, we're actually going to write multiple records, up to 1 million at a time. So if we expand using SQL Server Management Studio, if we look at the We have a new database called TestDB, and under tables we have a new table called remote data. Let's query that table. And just so we can order the data by date and time, that'll give us an organization to it. And so here we can see, going into the database engine itself, every sample, 1 per millisecond, is being inserted into the database. Now we can also visualize the data in a web or .NET application, and even look at historical data from a remote or local system as well. So let's show that in action. I'm going to use a web browser, and I'm going to hit that Raspberry Pi device to bring up what is the Web HMI dashboard that's built within the at each OES engine itself. And there we can see a live visualization of some live data on the system. Of course, it is bidirectional, so I can interact with it to open and close valves. Maybe turn this pump off. We see also trend and alarm information available directly from that device. With the trend information, it's to whatever resolution that you would like it to be. We can also run a .NET application looking at that same remote device. Here we can see I'm connected also to that same IP address. And one of the advantages of a .NET WPF interface, it is scalable. So I can shrink this down so we can see both interfaces at the same time. We have the alarm data that matches the alarm data through the web interface, and we have the trend information. Now, the alarm and trend information can also be historical data as well, but we're looking at live data that's being cached on the system. So the reason that I'm showing you this is another advantage of OAS is it runs as an edge solution, not a cloud solution. We can push data to cloud systems if you like, but because we're running as an edge solution, what will happen is if we have, say, a network failure to the OAS engine that we're doing the data logging, or also a failure to, say, the visualization for the trending and alarming, that data will still be able to be cached at the OAS engine. So if we look at the correct data representation of where we've been able to deliver the data, if we have a network failure, that all of the data would reside just locally on that system. Now what I'm going to do is I'm going to disconnect the cable from the Raspberry Pi device, and we see that we have a network failure showing the communication status on the operator interface is now showing a failure quality. That's all of the items are shown in yellow. If we go back to the database engine and we query that database itself, we see that the very last record that we've been able to achieve from that Raspberry Pi device is at 23 and 20 minutes, 5 seconds, and 291 milliseconds. So let's copy that to keep that handy. So what we're going to do now is we'll plug the network cable back in just a second. So during the downtime, we're able to buffer and achieve data processing for the alarms and the trend and the data archiving right on the device itself. So we have store and forward functionality built into that OAS engine. Now if I plug the network cable back in, we see we have the data coming back immediately. It's of course interactive again, that we'd like it to be. On the trend interface, we see that during that downtime of that network failure, the OAS engine was able to process all of that data there locally, and also any alarm conditions that occurred during that network failure were also correctly identified, and we've been able to record those as well. So if we look back at our diagram, we have now resolved the issue with the HMI interface connection, and we've also been able to resolve the connection to the database engine the data logging engine that's doing the recording. So that data would then be able to be delivered both to the local database data logging processing engine and also to the operator interface. So all of the data has been passed forward from the Raspberry Pi device during that temporary network failure. So now if we go back to the database engine, and if we can remember this time at 5 seconds and 291 milliseconds at 20 minutes, that is. Let's execute that database again. Let's find that time at 20 minutes and 5 seconds and 291 milliseconds. So if we find that particular record, that is the last record that we'll be able to achieve during the downtime. There we are. And that was the value that we had at that time, was at 91. And then we see the very next sample during the store and forward functionality being buffering. We see the next value is at 92. So you can see there was no data loss during that temporary network failure. And of course, we have all the records going forward of that system. Now you might ask yourselves, how would you be able to achieve such a high-speed data rate, say from a controller like an Allen Bradley controller, Modbus communications, maybe it's a Siemens S7 controller, or maybe it's even from an OPC UA server or even a classic OPC server. Well, OES has built within it. Remember we talked about that it has first in, first out data processing, and we process every single value and deliver every value as across the network, not just the latest value. So as the data is being brought in, we're able to process all of these data sources directly down to 100 nanoseconds as they are able to deliver it. In a moment, I'm going to show you a .NET application that can even go at 100 nanoseconds and log the data at that rate. In the communications to a controller, we have the ability to do some handshaking with some unique data handling. And so when we look at under the data logging communications, we have the topic called log buffer data from a PLC or a controller. And in that article, you'll see a video that demonstrates this technique. That what it does is you set up in the controller arrays of data that you want to log, and then you also set up a handshake, both a confirmation and error feedback, that will send to OES that the data is ready to be logged. It captures all of the values with the timestamps that you provide, and then it will record that and then let the controller know that we're ready for the next series of data. So you may have multiple sets of arrays or just one single array that you're filling, queuing up, and then passing on to OES. So controllers can go at usually 1 to 2 milliseconds, but if you need to go even faster, what we can do is we can use what is called the .NET programmatic interface with OES. And what I'd like to do is demonstrate that for you now to run at an even faster rate. From our website under the knowledge base, you can learn more about how to set up programmatic real-time data access. And the topic that I'm going to refer to right now is a simple method called write tags. If you look into the programmatic interface section for real-time data access and you see how to write data, here we have the write tags method of the OES data assembly. Now the OES data assembly can be used on a .NET Core application, or it can also be used in a .NET Framework application. And this application can even run remotely, and I'm going to demonstrate that for you now, of sending 1 million values in one call to our Raspberry Pi interface. So just going back to our diagram, here we have our .NET application. We're going to collect 1 million values. We're going to send those 1 million samples to the Raspberry Pi interface, and then we're going to pass the data through the network back to the OES engine. So we're demonstrating high-speed network throughput from the .NET application to the remote engine, and then from the remote engine onto the data logging engine. And then we'll also show the benefit of the efficient data logging to log 1 million values in one call to a local or remote database engine. So let's set that up really quickly. Back on our Raspberry Pi device, I'm going to connect back to it under Configure Tags. And I will change that data source of that A tag to value. And just to look at the code that we're going to actually execute in this application, we've got this set up to process 1 million values in a simple loop. We're going to set up the tags that we're going to write, and those tags are that tag is going to be a remote tag to that Raspberry Pi device, to this A tag that we just set up. And then we're going to basically increment the value to be logged starting at index of 1. And then we're going to add 1 tick to each timestamp. Now that's the key to getting the high resolution from a .NET application, is when we call the write tags method, you see that not only are we passing the tag names and values, but we're also including the timestamps, our timestamps that we want it to be as it's being recorded. So let's go back to our database engine, and using SQL Server Management Studio, I'm going to clear out our table. And if we query our table, we see we have no records within it. So now let's run that high-speed data application. And in that high-speed data application, what I'm going to do is when I click the Set Data button, I have now written 1 million values, 1 million samples to the Raspberry Pi database engine. We have recorded the start time and then the end time, and this just elapsed over basically 0.1 seconds. So 1 million records going at 100 nanoseconds each equates to 0.1 seconds. So now if we come back to the database engine and we query that table again, it's going to take a little bit of time to get the values back out of the database engine. Of course, a lot longer than it was to actually insert the records into the database engine itself. But in a moment, we'll see that we have 1 million records that have been processed and recorded into the table. So now we can see in the database table, we have 1 million records, each with 100 nanosecond timestamp between each, and each of the values that we've incremented. So if we go to the very end of the table, we can say that very last value is 1 million. And that's what within the code, what we had done is to increment each value by 1. Another common failure that you might encounter is a connection problem to the database engine. If the database engine, say, was remote, or if the database engine was in a maintenance mode, it may not be available. Well, the OES engine is going to buffer data in that scenario as well. We can set up the store and forward functionality also for the database engine as well. So on both the data source and data destination systems, we can set up under the configure options into this store and forward tab what directory we're going to actually buffer data to. Earlier we demonstrated a network failure from OES engine to OES engine on the Raspberry Pi device. It had set up to buffer data to its own local disk. Let's go back to the Raspberry Pi device and configure the tags on that remote system. And back under the A tag, we'll set it back up for a simulation. Back to log values each 1 millisecond. So now currently, if we come back to the database engine itself and we run a query on that, we see that the values are being recorded from the remote Raspberry Pi device. Now what I'm going to do is I'm going to stop the database engine to replicate a remote database engine failure. So I'll actually just put a stop to it. Now, during the time that the database engine is down, if we go into that buffer directory that we'd specified under Configure Options, we'll look to see that we have a buffer file there. So during the database engine failure, the system is now going to buffer data that is being collected to its local disk. That would also occur if we were reaching out to a remote database engine on the Raspberry Pi itself, and let's say there was a network failure. It can also buffer data directly to its own local disk. So let's start the database engine back up. And our downtime, we should note that the time, the current time on the system, actually let's just grab that off the Raspberry Pi directly here. We can go to just create a new tag called B, set its data type as a string, and we'll just look at the time as a date and time itself. So on the Raspberry Pi device, it is at 48 minutes and 8 seconds. So let's go find that in the database engine after we start it back up. So we'll start the database engine back up. And we're going to see these files disappear. And now we see that those files have been processed one at a time, not to overwhelm the network. So let's go back to query the database engine itself. So let's query that table. Ordering by date and time. And remember that time that we had was at 48 minutes and 8 seconds. So if we go down to that time frame, we look at 48.8, and we can see during that time, and of course that the time that the database engine was in failure, we've recorded all of the values. We've held on to that in the stored forward functionality and then delivered it to the database. So that's at the 8-second mark, 48 minutes and 8 seconds. And then, of course, 48.9 seconds. That would have been the time that the database engine indeed was down. And then going forward, all of the data is available. And now, of course, it's restored itself. Now, what if you have a communication failure back to the data source itself? Remember we talked about the obtaining values from the controller in a buffered format with that article talking about logging buffered data from a controller or a PLC. If you had, say, a controller failure during that downtime, and we're using that technique to log from a buffered data, the controller itself would be able to cache and buffer the data locally during that downtime. So that would be able to be easily to be handled. So let's say in this scenario, while we're not able to talk to the controller, it's received the data from the data source. It now has it buffered so that when the communications is reestablished to the controller, we would then be able to pick that back up. Or another way to handle that is you can have OES set up for failover mode as well to a secondary controller. So built into the communication drivers is a redundancy communication failure, so you can have a second parallel path as well. So as that problem would be resolved, it would be able to collect the data from the controller and then of course pass it on to the user interface and the other data logging engine itself. So we've accounted for all kinds of failure scenarios, but also demonstrated the high accuracy down to 100 nanoseconds of how OES transfers and processes data across the network and onto a database engine. And you can see that we have at no point any backup issues. So because the data processing is so efficient that we're able to process 1,000,000 records in a tenth of a second and be able to push that onto a database engine. And in your scenario, you may not need data at this rate. You might be logging levels or temperatures at a much slower rate. But it's important to know that the accuracy is there for your data models. You're going to want to have a sampling interval that's at least 7 times faster than the time cycle of the process itself in order to build an accurate data model. And so OES provides the highest accuracy for any IoT solution of collecting data from a data source of any industry 4.0 data source, that is, and delivering that data to the database. And this, of course, we're demonstrating it across the network, and it can be even across the internet, because all of the communication packets are encrypted and compressed. And so even though we're delivering every single value, it still is a much lighter communication packet throughput. If you'd like to try open automation software for yourself, visit openautomationsoftware.com, go to the download link, fill out the form, and you'll receive a 30-day demonstration mode. And it's fully functional, operational, so you can set up all of your various data sources that you'd like to connect to and define your data destinations of where you want to send that data to. We've demonstrated data logging and some of the visualization for web and .NET, also for trending and alarming, but you can also do alarm logging, data logging. Of course, we've demonstrated you can do alarm notification. You can even send data and share data across the network or internet to Microsoft Excel workbooks and on to third-party cloud solutions like Azure IoT, you can send data to AWS and of course to MQTT brokers. OES also has its built-in MQTT broker that's extremely high speed, the highest speed open broker that you will find available. And all you have to do is just define the data source at OES, and then you'll be able to pick that data up from that third-party MQTT client as you like. If you have any questions, feel free to email us at support@oesiot.com, and you can see that under our Contact Us page, where you can either call us or send us a direct email, or you can fill out this form and we'll reply with whatever inquiry that you might have.